Hello and welcome to today's lesson looking at stopping distances. Now this lesson is suitable for students carrying out AQA, separate science, physics, and we're going to be looking in the forces module in today's lesson. So we're going to try and calculate stopping distances when objects are braking. So we're going to try and understand what a stopping distance is and state what various stopping distances are, detail the factor that affects the stopping distance of a vehicle, in detail the work done when a braking force is applied to a moving object, which falls into the following part of the AQA separate science physics qualification. So 4.5.6.3 forces and braking. So we're going to be focused on stopping distances, reaction time, which includes a little bit of a separate science only content. So there's a little bit extra for separate science here, and then we're going to look at the factors affecting the braking distance. So consider a moving vehicle such as a car. If we wish to stop the car from moving, we've got to place a braking force on the car. Now, this is a resultant force used to decelerate the car to a stop. Now, the braking force acts against the motion of an object, so it can come from the frictional force between the brakes and the wheel, and it can also be the air resistance acting upon the vehicle. So the braking force needed to stop a vehicle in a certain distance depends upon a couple of factors. The first factor is the velocity of the vehicle when the brakes are first applied, because the greater the velocity, the greater the deceleration or negative acceleration needed to stop the vehicle, so the braking force must be greater. This comes from the equation Newton's second law of motion, F equals ma. If A is bigger, F will be bigger. So the greater the deceleration, the greater the braking force for the same mass. But the second factor that the braking force depends upon is the mass of the vehicle, because the greater the mass, the greater the braking force needed. Now this is again from the equation F equals ma. The greater the n, the greater the mass, the greater the F, the greater the braking force for the same deceleration. So we have two factors which can affect the braking force needed to stop a vehicle in a certain distance. So factor one, the velocity of the vehicles when the brake is first pressed, and secondly, the mass of the vehicle which is braking. Now, stopping distances show the shortest distance a car travels once you've seen a hazard in the road to when you stop moving. Now, these are very important to know so you can judge how far you would travel if you broke at a particular speed to see if you would actually crash your vehicle or you would knock someone or something over. So there are some general guides for stopping distances for vehicles on UK roads for different speeds which need to be memorised for your UK theory driving test. So when you're studying for your driving license, you need to be aware of the different stopping distances for different speeds. But we split the stopping distance into two separate categories. So the stopping distance of a vehicle is the sum of the distance the vehicle travels during the driver's reaction time, the thinking distance, and the distance it travels under the braking force, the braking distance, which can be shown with the following equation. Stopping distance is equal to thinking distance plus braking distance. So for example, if the thinking distance was 20 meters and the braking distance is 45 meters, the stopping distance would be 65 meters. If the thinking distance was 30 meters and the braking distance is 55 meters, the stopping distance would be 85 meters. And if the thinking distance was 40 meters and the braking distance was 75 meters, the stopping distance would be 115 meters. So the thinking distance is the distance the vehicle travels during the driver's reaction time, which can be affected by things such as tiredness, drugs, and alcohol, and distractions can also affect the driver's ability to react. So for example, using your mobile phone, having a conversation with someone, and a reaction time varies from person to person, but the typical values range from between 0.2 seconds to 0.9 seconds. The braking distance is the distance the vehicle travels under the braking force. So it can be affected by adverse road and weather conditions and the poor condition of the vehicle. So adverse road conditions include wet or icy conditions, and you always can only think about the poor condition of a vehicle as either the vehicle's brakes or the tyres. So as mentioned previously, the braking force and therefore the braking distance is affected by the mass of the vehicle and the deceleration of that vehicle. So the speed of a vehicle will affect both the thinking distance and it will affect the braking distance. Because the higher the speed, the greater the distance travelled for the same reaction time, the greater the thinking distance. So the speed and the thinking distance increase linearly. They increase in direct proportion with each other as the reaction time stays constant. The higher the speed, the greater the distance travelled for the same braking force, the greater the braking distance. Now the speed and the braking distance increase at a faster rate as the brakes are transferring energy from the kinetic energy store of the vehicle. And because we know the kinetic energy store is E equals a half mv squared, an equation you learned in the energy module, this shows us that as speed increases, the work done and therefore the braking distance increase as a square of the increase factor. So as the speed doubles, the work done and braking distance increases by a factor of 4, 2 squared. As the speed triples, the work done and the braking distance increase by a factor of 9, 3 squared. So it always increases by a square of the factor that it's increasing by. Now the speed limits are really important as the speed affects the stopping distance so much, and to avoid an accident, drivers need to leave enough space between the car and the one in front so that if they have to stop suddenly, they'll have enough time to do so safely. So let's just recap what we've learned. The shortest distance it takes for a moving vehicle to stop after spotting a hazard is called the stopping distance. This is affected by two factors: the distance the car moves from when a driver observes the hazard to pressing the brake, the thinking distance, and the distance the car moves after the brake is being pressed until it stops moving, the braking distance. And stopping distance is equal to thinking distance plus braking distance. Now, as mentioned previously, you've got to be able to discuss how distance for a vehicle to make an emergency stop varies over a range of speeds typical for that vehicle. So we said before, the thinking distance increases in direct proportion to speed, but the braking distance squared increases in direct proportion to speed. So as the speed of a vehicle increases, the braking distance increases at a greater rate than the thinking distance. So this is shown in the following example. When a car is travelling at 30 miles an hour, the thinking distance is 9 metres, the braking distance is 14 metres, so the overall stopping distance is 23 metres, which is approximately 6 car lengths. Now, by the way, this information comes from the highway code information for stopping distances in good weather. So just to clarify, these values actually increase in bad weather. So if for example, you're going 30 miles an hour in bad weather, in icy conditions, in rainy conditions, that you will look to have actually about a stopping distance of about 30 meters. Now, what about a car speed at 50 metres? Well, the thinking distance is 15 metres and the braking distance is 38 metres, so you get an overall stopping distance of 53 metres, which is approximately 13 car lengths. So you can see, whilst the thinking distance has increased, the braking distance has increased by a much greater value. And then we look at 70 miles an hour, and then at 70 miles an hour, the thinking distance is 21 metres, the braking distance is 75 metres, so the overall stopping distance is 96 metres. So you'll see that the braking distance has increased at a much higher rate than the thinking distance. So now at the higher speeds, there's a greater proportion of that stopping distance is due to the braking distance than it is at the lower speeds. So we can plot a graph of vehicle speed against stopping distance, and as you can see with this particular idea, all vehicles have similar graphs for speeds against stopping distances, and the curving nature of the graph is due to the rapid increase in braking distance with speed. So you'll notice that the reason why it's curving is due to the braking distance, because as shown on the graph, the thinking distance is in direct proportion to the speed because it's a straight line through the origin. Now, we can actually find the difference in stopping distances for vehicles by using these graphs. So how to do this is you look on the graph to find the stopping distance for a speed stated in the question for the vehicles, then you find the difference between the values. So for example, a question might ask you is to find the difference in stopping distances at 50 miles an hour. So what you do is you go onto your graph and you find your different stopping distances for each object or each vehicle. So one is at 40 meters, one's at 70 meters, so therefore your difference in stopping distances is 30 meters. So here are some sample stopping distances carried out by standard cars in the UK in good weather. So at about 20 miles an hour, we've got a stopping distance of 12 meters split evenly between thinking and braking distance. At 30 miles an hour, we've got a thinking distance of 9 meters and a braking distance of 14 meters, leading to a stopping distance of 23 meters. At 40 miles an hour, we've got a stopping distance of 12 metres and a braking distance of 24. So now the braking distance is double that of the thinking distance, giving a stopping distance of 36 metres. At 50 miles an hour, the thinking distance is 15 metres, the braking distance is 38 metres, giving a stopping distance of 53 metres. At 60 miles an hour, the thinking distance is 18 metres, The braking distance is 55 metres, leaving the stopping distance of 73 metres. And then at 70 miles an hour, the thinking distance is 21 metres, the braking distance is 75 metres, so now significantly higher than the thinking distance, leaving us a stopping distance of 96 metres. So what conclusions can we make? That number one, the higher the speed, the higher the stopping distance. Number two, the braking distance increases by a greater amount than the thinking distance, and that the braking distance naturally makes up a larger part of the stopping distance than the thinking distance does, and this only increases at higher speeds. So, we now move on to what happens when we actually apply this braking force. So when an object such as a car is moving, they can be decelerated by placing a braking force on the object. So that's the resultant force placed on the car from the brakes, and this resultant force causes deceleration. So this can be calculated with the equation F equals ma. So the resultant force will cause the energy to change type of store in the system, as well as it causes them to decelerate. So here, the resultant force, which is between the friction, which is the friction between the brakes and the tyres, causes work to be done. What's happening is work is being done by the frictional force between the brakes and the wheel. So this resultant braking force makes the kinetic energy store of the car change form. So this energy is transferred from the kinetic energy store of the vehicle to the thermal energy store of the brakes. This causes the temperature of the brakes to increase. So as the energy store of the car is changed with the resultant force, we say that work is being done. There is mechanical work in place. Now, when there's a large braking force applied to a car, the car brakes glow red, as it's now a large thermal energy store. This means that the brakes are extremely hot, which you can observe on certain race cars. Now, eventually, the thermal energy store of the brakes is then dissipated to the internal energy store of the surroundings. But please remember that the larger the deceleration, the larger the resultant force needed, the more energy transferred to the thermal energy store of the brakes. So this therefore begs the question that if there's a larger deceleration, the larger the resultant force needed, the hotter the brakes become. What happens at extremely large braking forces when you have an extremely high deceleration? So if there's a large enough deceleration, which needs a large enough resultant force, the brakes will contain so much thermal energy they will overheat and set on fire, which you can sometimes observe in race conditions for cars observed on this particular animation. Now, the greater the speed of the vehicle, the greater the braking force needed to stop the vehicle in a certain distance, so therefore the greater the braking force, the greater the deceleration. But this can also lead, as well as the brakes overheating, to a loss of control in the car, which can cause the car to skid, which is shown in these particular animations. So the large change in kinetic energy store causes the car to lose traction with the road, leading to a skid. Now we've got to be able to estimate the magnitude of the force which causes these objects to decelerate, which can be done by combining a couple of equations. Number one, you use the equation v squared minus u squared equals 2as to work out the deceleration of the object. You then use the equation F equals ma to find the resultant force of the brakes. So that will then allow you to work out what this braking force is. So let's just recap what we've learned. When a force is applied to the brakes of a vehicle, work is done via friction between the brakes and the wheel to transfer energy from the kinetic energy store of the vehicle to the thermal energy store of the brakes. The greater the braking force, the greater the deceleration of the vehicle, but a large deceleration can lead to the brakes overheating and or a loss of control of your car. So let's just summarize this entire topic of stopping distances. Friction and air resistance oppose the driving force of a car. The stopping distance of a car depends on the braking distance and thinking distance. High speed, poor weather conditions and poor maintenance all increase the braking distance, whilst poor reaction time and high speed both increase the thinking distance. Reaction times vary from person to person, but typical values lie between 0.2 seconds to 0.9 seconds. The driver's reaction time can be affected by tiredness, drugs and alcohol. Distractions may also affect a driver's ability to react, but the braking distance of a vehicle can be affected by adverse road and weather conditions and poor conditions of the vehicle. But adverse road conditions include wet or icy conditions conditions, but a poor condition of a vehicle is only limited to the vehicle's brakes or tyres. When a force is applied to the brakes of a vehicle, work is done by the frictional force between the brakes and the wheel, reducing the kinetic energy stored in the vehicle, and the temperature of the brakes increase. The greater the speed of a vehicle, the greater the braking force needed to stop the vehicle in a certain distance. So the greater the braking force, the greater the deceleration of the vehicle. So large decelerations may lead to brakes overheating and or a loss of control. So if we've been successful and we've learnt in this lesson, we can understand what stopping distance is and state the various stopping distances. We can detail the factors that affect stopping distance, and we can detail the work done when a braking force is applied to a moving object. I hope you've enjoyed this lesson looking at stopping distances, thinking distance, braking distance, and then the work done when a braking force is applied, and have a lovely day.